All right.
So we're not like.
All right, guys.
But we're thinking we might do.
I did say quarter past, so we're gonna do it. I'm still missing some people. But I won't. It's their choice. So there's something. There's something where that there's nothing wrong with what we've been doing, but we have to kind of build on it somehow, because every problem we've done so far that used the z-score chart, I want you to go back and realize this. We were always picking one person or one thing. What's the probability that thing was greater than this, less than that? You guys with me? So that sheet, let me see if I have a copy of it. Yeah. This sheet. Find the probability that there means. So if we randomly pick one student, what's the probability they took this much time, that much time? You with me? If you look back at every problem we've done, that's been what it is. Pick one thing. Nothing wrong with that if that's the situation. But what do we normally do in statistics? What do we normally work with? Sample. So we have to somehow figure out, if I didn't just pick one, if I picked a sample of things, how would things change? So let me ask you this. Let's talk about the general, like a feel for the idea first. If I went out right now and randomly picked somebody and they were taller than 6'6", that would be kind of a little unusual, right? They'd be like, okay, whoa. If I went out and took a random sample of 20 people, and their average height was 6'6", you'd be like, where the hell am I? Is there a convention in town? Huh?
You're probably like a basketball.
Basketball maybe, or a convention of people that are tired of hearing, well, how's the weather up there? That kind of shit, right? You guys kind of with me? A little bit? So, we're going to do, all right, if you don't know this about me yet, I'm going to explain the idea insane amount. And that's just the way it's going to be. I can't change it. But then we're going to do some concrete stuff. What does it actually change? It changes very little. It's really nice. It barely changes anything. But I still have to explain the idea. Okay. So the way I like to do this is alternate universe Florida. Okay? Or if you don't like that, there's just a state. Let's say there's just a state where this is what the ages look like. The ages look like 0, let's say to 100 just to make it, and I get, all right, let me let you just absorb that for a second. I got mounds of people. I just pile them up like World War Z. They just all. What does this mean? Who are these people? They are very young. I like it. And then I got the retirees up here, which basically sort of summarizes Florida, which is why it's such a weird place. I can say that because I used to live there. Oh my God. Yeah, the ground doesn't go up; it goes down when there's a sinkhole. So there's nothing interesting to see. Is there anybody in the middle? What would be your best guess for the mean, just based on what I've shown you here? I mean, my best guess would be 50, right? Let's just pretend that really is the mean. I'd have to know what the data points are and all that kind of shit. Let's just say it is 50. Doesn't matter for this example. All right, I like it. So right now there is a standard deviation of ages, right? If I knew all the data points, I could calculate what it was. I'm not interested in what it is exactly. So how did I create this? I know I just made this shit up, but let's say this is really true. What would I do to start putting this together? I'd have to go to alternate universe Florida. And have to start doing what? Walking around and say, asking how old are you? And if I'm not very I'd say, let me see your ID, right? And I put on some uniform I bought. And I'm like, let me see your ID. Okay, keep going. And so I'd ask somebody, how old are you? I'm 2. you know. How old are you?
Not yet.
All right. You with me? And then I would just start, and I just keep doing that until I got this picture. There's so many people that it kind of makes this little mound thing. Okay? Maybe. This isn't a perfect example, but this is a pretty good example. I like how this kind of comes out. Okay. How did I get 50 if that really is the average? I just added up all the people's ages divided by how many there are, right? Is that cool? Agree with me? Okay. So this is a sample size of 1. I picked one person and I plotted them. Picked somebody else and I plotted them. And let's say this has, so the mean is 50 and the standard deviation is whatever it is. Okay, now, stay with me. This is kind of cool. If I were to, instead of picking one person and asking each person their age, what if I picked a group of 20 people? And I said, what's your average age? Right, so I made them talk to each other and I calculate their average. And then they give me that number. And then I go plot that. And then I go to another group of 20 people. You guys kind of with me? So instead of asking one person at a time, I do 20 people at a time. So every dot I put on the picture doesn't represent an individual, it represents a group. Can anybody see what would be the most likely thing? Is the most likely thing that I get a bunch of 22-year-olds? Is that going to be very likely to happen? That I randomly pick 22-year-olds. 22-year-olds. Sorry. You with me? Sorry. That's why I'm pointing there. I just realized, I'm like, that's not really. So is it likely that I pick a group of 20 2-year-olds? Is that going to be very likely? How can you tell? Low there. It's not very many 2-year-olds, right? The most likely thing that would happen is a mixture of old and young. Right? You guys kind of with me? So if I pick 20 people at a time, I could get nothing but 2-year-olds, couldn't I? That's not impossible, but will that happen often?
No.
Hell no. What's going to happen more often is some kind of mixture from the groups, right? So to be honest, the most often average, the most likely average I'm going to get is that one, right? If I took a group of 20 people from this, what's your best guess for the average age? 50. Is any individual 50 years old in this population? No. But most of the samples will have an average of 50. Does that make sense? Because what's the most likely thing to happen? A mixture of old and young. So their average will be there. So if I'm going to start plotting points, instead of plotting points for one person, 2-year-old, 87-year-old, I'm plotting, when I plot a point, it's the average for a group of 20 people. How will that picture look compared to this one? Let me put it down here. Yeah, that's a little, all right. So it's going to look like this. Let me see if you guys kind of get this. It's probably going to have a little bit of a bump there, and a bump there. The most likely thing is going to be the 50. These little bumps are kind of like, because you could get a bunch of old people or a bunch of young people, because that's where most of the stuff is. Are you kind of with me? And any mixture is going to be in here. Do you understand that the average, again, tell me, what does that dot mean?
A sample of 20 people.
X bar of a group of 20. The sample mean of 20 people. Some group of 20, I put them right there because that was, so this is a picture of X bars. Okay, I like it. Maybe, and this is a picture of individuals. This is a picture of X's. Okay, maybe. The mean stays the same. The average of all the averages is going to be 50. So for example, and for some reason less and less people get this, but there's an average age in here right now. I know we've said this so many times. There's an average age in here right now. And how do I get it? I take each person, add up all the ages. If I took 2 people at a time took you guys average, and took you guys average, and took you guys average, and then averaged all those up, how the hell would it be anything else than what the actual average is? Just because I take 2 people at a time, does that change the ages? No. Do you guys get that? So if I take 1 person at a time, I get an average age. Just because I take 2 at a time, it's not going to change the average of the people in the room. I take 2 people and everybody suddenly gets older. Stop doing that, Mr. Wally. Right? No, it's not going to happen. The average stays the same. Just because I take groups at a time doesn't change what the average is. So that's why the middle, the 50, is in the same place. The mean of the sample means, oh shit. So in mathematics, whenever you have a subscript, that is a specific this. The most common place you guys remember you saw a subscript, for example, was this dude. What was this dude? Anybody remember what that dude was?
The slope.
Slope. What that little 2 mean? Second point's y, right? So that's the y from the second point minus the y from the first point. Subscripts just mean it's a specific this. It's not any y you want, it's the second point's y, and that's the first point's y, and so forth. You guys with me? So this means the mean of the sample means. That's all that means. Now how would this, so shit, gotta sneak it over there, aren't you? How would this compare to that? Which one is bigger? Is this spread bigger or is this spread bigger? Which one is, which, and again, what does standard deviation tell you?
The distance.
Average distance from the mean to all the data points. Which set of data gets further away from its mean on average? The top one. So this guy, sigma, is bigger than this guy. What happened to this data? Didn't it come to the middle? See how these are like, I don't like you, and then, oh. Didn't it come in? Do you guys see that? So if I take groups, does this make sense? Any individual person can be much older or much younger. But if I start taking groups of people, a whole group more than likely is not going to be really, really old or really, really young. It's going to kind of average out for the most part. So most things will be around the middle. And then less stuff outside. That means the standard deviation gets smaller. And to cut to the chase, here's exactly how much smaller this gets. It's the old standard deviation divided by the square root of how big the samples were. If I take a bigger sample, isn't that going to be closer to the actual average? Think about it. Right? If I take 2 people from here, their average age could still be really different from the actual average. If I take 20 people from here, more than likely their average is going to be really, really close to the actual average. They're going to kind of average out within that group. So doesn't it make sense that the bigger the samples are that I'm taking, the closer each sample is going to be to the actual average? Okay, maybe. Therefore, the middle doesn't change, but the spread does. The spread gets smaller. It's less likely for a group of people to be further from the average than it is for one person to be further from the average. And that was that example, Ariel, about the 6'6" person versus the 6'6" group. That 6'6" average group, I was like, whoa, holy shit. You see somebody 6'6", you're like, okay. You see a bunch of 6'6" people around 6 feet, you're like, what is happening? Right? So it's less likely for a group to have an average really far away from what the true average is. That's all this is saying. Groups are going to tend to be closer to their average. Maybe? All right, now, I actually have a very scary, but you don't have to do this by yourself ever, example. One of my most colorful handouts is like 2 colors. Good job, Joe. But, oh well. I'd like to show you a concrete example. This alternate universe Florida, we can't go there. So I want to give you something that's a little more concrete. So I kind of had to make it a small selection so it was something we could look at easily. Focus. Okay. So I have 4 pieces of paper in a hat, and they're numbered 1, 2, 3, 4. So of course they all have the same probability of me picking them out. Is that cool start? Right? And I kind of made them have a width just so it would be easier to see. So the idea I was talking about up here is exactly what's happening on here. I'm going to reach into the hat and pick 2 slips. So for example, couldn't I reach in and get 1, drop it back in, and get 1 again? So that means this picture was made by plotting the 1, the 2, the 3, the 4. And there's only one of each, so there's a 1/4 chance. Now I'm going to make a new picture based on the means of all the samples. So one sample I can get is 1, 1, and then 1, 2, and 1, 3. You guys with me? So I can actually see every single possible sample relatively easily because it's a small set of data. So this is my original data. And you guys could do this yourself if you wanted to. You know how to figure out the mean and standard deviation, xp of x, right? And blah, 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 blah. Maybe. Uh-oh. Hopefully you do. Okay. And so you could actually verify this. Okay. In fact, let's do this right now. Let's just do it. Let's do this a quicker way. What is my actual data set? What data do I have up here to start with? 1, 2, 3, 4. So screw the xp of x shit. Let's just get the average of these. And the standard deviation. How do I get the average and standard deviation of these things? Of a list of data. How do we get the average and the standard deviation? In the calculator. Because we're done with chapter 1, chapter test, first test. Second.
You got to
Stat. Calc.
And then you press enter.
One of our stats.
Yeah.
I love it. And then you make sure it's L1. All right, so the mean is 2.5. The calculator just defaults to X bar, but we know better. This is my population. And the standard deviation is 1.118. There it is, right? Is that cool? Okay, now stay with me. Now I'm going to say, if I take all samples of size 2, and here they all are, and the data isn't 1, 2, 3, 4 anymore, it's the sample means. So everything in yellow is my new list of data. So why don't you guys double check me here. Let's put this into list 1, put all this data in. So 1, 1.5, 2, 2.5, 1. Just put it all in there, or just sit there if you don't want to. Hopefully I've done this correct. Let's see. Oh shit, something's wrong. No, it's okay. Yeah, okay. So we get all that in there, and I calculate my one variable stats. The mean is still 2.5. Yes?
Show me your chart.
What do you mean? What? Here? So what am I doing? What's my new data going to be? The sample means. So everything in yellow, I'm putting in. So that would be what I plot on the picture. Not individual pieces of paper, but averages of 2 slips of paper.
Oh, so your other.
So my new data is now all of this. See how big that group got? I'm taking 2 pieces of paper from 4 pieces of paper, and it got pretty huge, right? So you can imagine how huge it would be for something like alternate universe Florida. What's up? How we doing? Now, just a disclaimer. This is a very weird idea. So if you are feeling that way, that's fine.
I was just wondering where L2, the other ones, those were just.
That was just leftover shit.
Okay,
Sorry.
that was-
I didn't clear them out. I just cared about list one. Yeah, all this other stuff left over from the other day. Or I think this is from me making the answer key for the quiz. So I guess. All right. So now if I do, I think I just did it, didn't I? Oh shit! What did I just do? Or little calculator. So if you do this one var stats on all these means, the mean is still 2.5. So the average of all the averages is still 2.5 like it was. So it's still 2.5. And the standard deviation is now 0.791. Now, do this. What was the standard deviation before for individuals? 1.118. Now theoretically, what should the new standard deviation be? The old one divided by the square root, and how big was each sample? 2. So if you take 1.118 divided by the square root of 2, you get 0.79 freaking 1, which is exactly what the actual new standard deviation is. That's always my hope. So there's nothing special about the numbers I picked. There's nothing. If I would have picked completely different numbers into this whole thing again, exactly this would have happened. Whatever the standard deviation was, divided by the square root of how big my samples were, becomes what the new spread is. And of course, mathematically, since I'm dividing by something bigger than 1, it's always going to be smaller. And what is that? How does that relate conceptually? If I take groups, they should be closer to the average. That means the spread should decrease, which means the standard deviation should get smaller.
So the spread decreased from this one?
Yes! Do you agree with me? Which one is closer to its average more often? Well, look, the biggest bar is right on 2.5. So this one is at its average more often than this one.
That one's just.
Yeah, this one, equal amounts get really far away. This one, not nearly as much, gets really far away. So this spread is much less than this spread. Not much less, but it's definitely less. Which one is more normal? The bottom. I like it. That's the next step of this. Okay, love it. Now, as a student, you see a worksheet like this, and you're like, holy shit. I would never be able to, what did I say when I gave this to you? You're never going to have to do this. This is me giving you a concrete example that you can see everything that was related to this. That's exactly the same thing I was talking about up here. Just up here, my population is stupid big. There, I wanted to give us a nice little tiny population, 1, 2, 3, 4, so I can see everything happen. So this is me going and talking to 2 people and saying, what's your average age? 2.5. Calculate it, kid. So. Maybe. Yes?
But the difference between like the first chart here and that one there is that you didn't have anything in the middle.
Beautiful.
And in here and then
Exactly.
that one you do.
So here's the next level. So now I love it. You kind of pushed me to the next step. So what do we know so far? If I take a sample of data points, the mean of the means stays the same as the mean of the data points. The standard deviation changes based on how big my sample was. Right? And the result becomes more normal. Is this normal? Eh. Is it more normal than this? Yeah. And here's the magic number, right? Let me consolidate what we know and give it a name. This is called let me consolidate it first, and then I'll tell you what it's called. So we know the mean of the sample mean stays the same as what the data points were themselves. Because I didn't change the data, I just took them in groups instead of individually. Why would the average become bigger or smaller? That doesn't make any sense. But the spread of those data points definitely changes. So here's what I always say. This is the spread of individuals. Individual data points. Whereas this one is how spread out groups of data points are. So when you get a question that says, what's the probability that a group of 37 people will have an average blah, 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 you got to use this standard deviation. Why would you use standard deviation for individual data points when you're talking about a group of data points? You can spell, Jeff. I've seen you do it. All right. And the third thing is, as n gets larger, distribution gets more normal. Now, if it starts off normal, it can't really get more normal. It does get skinnier because of this thing, right? But if it starts off completely weird as shit, here's the really cool thing. The magic number to get to is more than 30. If n is greater than 30, the result is approximately normal. Why is that so important to know? Because what was this again? This was a collection of answers. What's the only time you can use it? If your distribution is normal. Now we have a check for situations to see if it's normal enough to use this chart. If n is 27 and it doesn't say anything else, I can't use this chart. Too bad, so sad. But if n is 33, yeah, I can use this chart. I know it's officially normal enough. So I'm going to say that phrase a lot this semester. Normal enough. Yes? If n is greater than 30, the result, yeah, I really started using hieroglyphics there. The result is approximately normal. What I mean by that is when you plot the averages of more than 30 sample size groups, they will become normally distributed.
And that's general, like the N 30?
For questions about means.
Okay.
We're going to have questions about percentages later, and it's going to have a different check.
Okay.
Yeah. This whole thing, this thing, all these is called the central limit theorem. So as I take larger and larger samples, all the means start to go closer and closer to the middle. So the limit as my sample size goes to infinity is going to be the center of the data. All right, that's where they're all kind of headed. That's where the name of that theorem comes from. Not important, but I just want to tell you. They're kind of going towards the middle. Central limit theorem. So now, yeah, all of this has been explanation of idea. If I'm in this class, I'm like, what does this mean for me, Jeff? What kind of problem? What would the problem look like, man? All right, so let's do a problem that incorporates this. So I promised you earlier, it's going to be very slight nuts and bolts change. Concept is kind of crazy. I had multiple things I did to explain this idea. The work is really nice. That's what I hope you agree. Okay, here we go. Let's try an example. So I hate to start a lesson with trigger points, but I don't mind getting there after making you go through the whole idea. So what do I mean by this? How do I know when to shit to do this? How do I know when to do this? And I already answered that question, but it's when I'm not talking about individuals. What is this problem talking about? Is it talking about individuals? No, it's talking about groups of size 39. This standard deviation is only for individual data points. Can I use it then? No. Let that make so much sense. When do I change the standard deviation? I'm sorry. Put that on. When do I change the standard deviation? When the question is talking about groups of things. So there's two things actually to really make sure you're in the right situation. I take a sample and I ask a question about the mean of that sample. Those two things say, oh shit, I gotta change the spread. I got the wrong spread.
Wait, can you say that again?
Sure. If a problem takes a sample and then it asks about the mean of that sample, like a probability of the mean doing something, I've got to use what I call the new standard deviation. So this is the spread of groups. I can't use the spread of individuals for a question about a group. I'm looking at some of your eyes at 11. It's like, good Lord, every day something can happen. Holy shit. I really want this to make some level of sense. That idea that the spread changes, and therefore if I want to do a question, like what am I going to do to do this question? I'm going to make a z-score, I'm going to look it up. And how do I make a z-score? I divide by the spread. So I better use the right spread. This ain't the right spread for this problem. I got to change it to become a spread for groups, not a spread for individuals. So when we did the earlier problems, and I picked one person, I said it was normal, didn't I? Every time. I had to. Because the sample was only 1. It's not bigger than 30. I had to tell you it started off normal, so the sample size didn't have to say my ass. Right? And then what's probably that one person is above